Okay. So for part 1, we are asked to come up with a method that can detect at most k malicious errors. Now, one thing that I want to point out is that malicious errors are errors that can happen at any point, and our method should be able to detect them if they occur at any point. In contrast, non-malicious errors are kind of like random errors that are produced by the nature, and we don't really care about detecting them in all of the cases. We mostly care about detecting them in most cases, since we can assume that nature is not going to be evil towards us and break our method at the points where it's weak. Okay, so for part 1, we are going to protect against malicious errors. Okay, so one idea is to use the same method that we've been using for error detection in the case of for error correction in the case of erasures and also errors, which was if we have a message that consists of n different symbols, we first find a polynomial of degree at most n minus 1, like p of x, such that degree of p is less than or equal to n minus 1, which passes through those n symbols, meaning that p of I is the ith symbol. Okay, and we know that such a polynomial is unique, right? Okay. Now, the way we used to do it was we extended this polynomial to some number of extra points. Let's call that number L. So we extend our original message by L symbols, and we send p of 1, p of 2, up to p of n plus L. This is going to be our extended message that we sent. Okay, so let's see what happens in our case. When are we able to detect errors and when are we not? Okay, so first of all, note that if L is less than or equal to k minus 1, then in that case we are sending n symbols here, and then we also have at most k minus 1 extra symbols here. Okay, now suppose that an evil guy is changing our symbols, and he's gonna first change the last symbol we had here in our message, and he's gonna change it to something else, like this value that I'm gonna represent by a square, and then he is gonna figure out the unique polynomial of degree at most n minus 1 that passes through the first new n symbols, meaning that he's going to be able to find the polynomial q of x, which is of degree at most n minus 1, which passes through the first point, the second point, the third point, and so on up to the nth point, the new nth point, which is the square. And then this guy is going to be able to extend this message, this corrupted message, by k minus 1 symbols. So he's going to be able to figure out what q of 1, q of 2, up to q of n plus L are, right? And of course, our algorithm, if it receives this thing, it's going to think that the original message was the one that was produced by q of 1 up to q of n, right? Because that was how we decoded it. That was how we kind of encoded it, right? So our algorithm, no matter how it's going to be detecting errors, it's going to take these two to be kind of equivalent, and it's not going to be able to detect this, right? Because if the original message was actually the corrupted message, which consisted of the first n minus 1 symbols plus the extra corrupted square, then the encoded message or the padded message would have been looking something like this, right? So our algorithm doesn't know that this is the corrupted version of this. Okay. So now, how many symbols did we corrupt in order to go from this to this? Well, we didn't corrupt q of 1 up to q of n minus 1, and we corrupted everything else, right? How many extra symbols are there? There are at most k minus 1, but we also corrupted one extra thing at the end of our original message, which was here. So we corrupted at most k different symbols, okay? And so we satisfied our constraint that we can corrupt at most k different symbols. Okay, so that shows that no matter how our algorithm works, it's not going to be able to detect up to k errors if we use at most k minus 1 extra symbols. Okay, now let's see why if we use k extra symbols we can detect errors. So here we are assuming that L is equal to k, and we want to be able to detect errors. First of all, how are we going to do that? Well, we're going to take the first n symbols that we receive. Then we are going to construct a polynomial q that passes through them, meaning that q of I equals the ith symbol for I between 1 and n. And then we are going to check that q also passes through the extra k symbols. Okay, so we are going to check whether q of I is equal to the ith symbol for n less than I less than n plus k. Okay, if this happens to be true, then we say that no error has occurred, and if it's not true, then we say that an error has occurred. Now, of course, if in reality no error, there was no error, then our algorithm would say that there was no error, obviously, because it would receive exactly these values, and the polynomial q would be exactly the polynomial p, and so on, right? Now, let's see what happens when in reality some errors occur, okay? We are going to be proving that our algorithm would say that there was an error, meaning that this thing would not happen, okay? So, in reality, some places are corrupted and some places are not, right? But we know that at least n places are not corrupted, because we can corrupt at most k different places, and we have n plus k places in total, right? So there are at least n different places that are not corrupted. Let's say those places are the places I'm referring to by these arrows. Okay. Now, there is a unique polynomial of degree at most n minus 1 that passes through these uncorrupted points, right? Because there are at least n of them. Now, this is the thing that I'm saying. If our algorithm by mistake says that no error has occurred, then this polynomial q, right, is going to be passing through all of the points, and we know that degree of q is at most n minus 1, right? Is less than or equal to n minus 1, right? So we have found the polynomial of degree at most n minus 1, which passes through all of the points, including the non-corrupted points that I'm referring to my arrows, right? But then p also passes through the non-corrupted points, right? Because p originally passed through the original symbols, and the non-corrupted symbols are the same as the original ones, so p passes through them. Okay, so p is also a polynomial which satisfies the fact that degree of p is less than or equal to n minus 1, and p passes through the non-corrupted places. But like I said, there is at most a unique polynomial. There is a unique polynomial of degree at most n-1 which passes through the uncorrupted points. So it must be true that p is equal to k. Now, since p is equal to k, and p is equal to q, and q passes through all of the points, it means that no point has been corrupted. Okay. So, in the case that our algorithm outputs that there has been node errors, we managed to prove that there actually was no errors. Okay. Now let's go to part 2. Okay. In this part, we're just using one additional symbol. There are many ways to solve this, the case for non-malicious errors. Let's go with what we had and just add the one extra symbol that we get from the polynomial introduced by the first endpoints, meaning that if we find a polynomial p whose degree is at most n-1 such that p of I is equal to the ith symbol, for I between 1 and n-1, and then we add exactly one symbol, meaning that originally we had p of 1 up to p of n, and then we add this one extra little symbol p of n plus 1. Okay? Now, in the case of non-malicious errors, the nature is going to be changing some of these symbols randomly, right? When we change some of these symbols randomly, the correct symbol that should be placed as the one extra symbol here is going to be some number, some random number between 1 and p, or 0 and p minus 1. Okay, the correct symbol is going to be some random thing between 0 and p minus 1. What do I mean by that? Well, how is our algorithm going to work? Well, our algorithm is going to work exactly like the previous part. It's going to first detect the polynomial of degree at most n-1, which passes through the first endpoints, and then it's just going to check whether it passes through the n plus first point as well or not. Okay. The thing is that if there are errors, then then there is going to be a unique value in the last place, in the n plus first place. That's going to be making our algorithm output yes, meaning that that's going to make our algorithm detect no errors. Why is that? Because obviously there is a unique polynomial here that passes through these points, and that polynomial has a unique value at the n plus first point. Okay, and the chance of that extra symbol happening to be exactly the same as our n plus first point is going to be pretty low. It's going to be almost 1 over p, right? So as long as p is a large prime number, which is assumed here, the chance of our algorithm not detecting this is going to be very, very small, 1 over p. Okay. Now there is also another. So for this to work, you should actually prove that the correct symbol for the n plus first point is going to be random, meaning that it's gonna any extra symbol, any number for this last place is gonna happen with equal probabilities. Okay, you can count that using methods that are defined by the lecture, but I'm actually gonna show you a simpler method which is gonna help you figure out why this n plus first symbol is random. So suppose that instead of using these polynomials and all of that, we made sure that the n plus first symbol that we introduce makes it so that the sum of all of our symbols, m1, m2, up to mn plus 1, is equal to 0 mod p. So this is like a checksum. This happens mod p. Then if some random errors happen at some points of our symbols, the sum of our symbols is going to change by how much? It's going to change by some random numbers that are added together, right? And each number that is added to so let's say that m2 is changed, okay? m2 is going to be changed to another symbol purely randomly, right? So if m2 was the only symbol that was going to change, then our whole sum would change by how much? It would change by exactly the amount that m2 changed, which is going to be some random number between 0 and p minus 1. Which is going to be some random number between 0 and p minus 1. And so our sum is going to only be equal to 0 with probability 1 over p, okay, which is pretty low. Now in the case that multiple symbols change, you're dealing with a sum of some random numbers, which itself is going to be random. So the probability that it's going to be equal to 0 is exactly going to be equal to 1 over p, which is pretty low when the prime number we are working with is large.